Hello and welcome to the notes for Chapter 8, Probability. So a lot of this slide are things that you either already know or have a vague idea about from year 7 and 8, but they do need to be said formally. We need to get used to the language of probability in GCSE before we do anything with it. The first word we've got here is trial. Trial is just something that you do. For example, flip a coin, or roll a dice, or see if the train's late. An outcome is something that happens when you do that trial. So if you flip a coin, the outcomes are heads or tails. There are two possible outcomes there. If you roll a dice, there are 6 possible outcomes. If you take the train, there's 2 outcomes if we're just looking at whether it's late or not. Then you have event. Event is if there's a combination of outcomes taken together. So for example, if you roll a dice, an event is roll an odd number, which consists of 3 different outcomes, a 1, a 3, and a 5. Because these are all equally likely events, we can come up with this general formula here for the theoretical probability of an event, which is the number of outcomes that make up that event divided by the total number of outcomes, full stop. So go back to our rolling an odd number example. The probability of rolling an odd number is 3, because there are 3 odd outcomes, over 6, because there are 6 total outcomes. Now we tend to write that using shorthand. We don't write the probability of an odd number on a fair dice. We use this little P bracket notation to say exactly the same thing. And we would summarize that as P, odd number on a fair dice, is 3 out of 6. I didn't mention the word fair there. That's really important in probability as well. Things that are fair are equally likely to happen. It's really important to have fair coins, fair dice in these events. You obviously can't have fewer than 0 outcomes in an event, so the lowest that a probability can get to will be 0 out of 6, or just 0. That would be an impossible thing. And you can't have more outcomes in an event than the total number of outcomes that are there. So a number divided by itself, the highest probability you can have is 1 for certain. I think these are all things that you already know, but they're important to state them first. Now, if we look at an example of using this sort of notation, we can ask some questions that, to be honest, you probably could have answered in year 7. We've got a fair 6-sided dice that's rolled and the top number's recorded. That is our trial. We're going to complete the tables of the outcomes that we could have, and thus the theoretical probability of those events. So probability of rolling a 7. There are 0 outcomes on a dice that would actually end up with you rolling a 7. We just go 1 to 6. So there are no outcomes to fill in here. So the theoretical probability of rolling a 7 is 0 out of 6, or just 0. Rolling a number less than 7, well, that's every single number. All of these outcomes, 1, 2, 3, 4, 5, and 6, are less than 7. So the theoretical probability of that is 6 out of 6, or just 1. That would simplify to impossible event, certain event. Then we get a little bit more grainy. Rolling a prime number. There are 3 prime numbers on a dice. Those are numbers you can't divide down, not including 1. So our theoretical probability of a prime is 3 out of 6. We could simplify that to a half, but you do not need to simplify probabilities unless the question asks you to. Lastly, you've got rolling a factor of 10. Now those are numbers that divide into 10, so we've got 1 and 10 and 2 and 5. So yeah, 1, 2, 5. There are 3 outcomes on a dice that are factors of 10. So our probability is 3 out of 6, or just a half. We could then say, well, what's the probability of rolling a prime that's also a factor of 10? Do we combine our 2 probabilities together here? Do we add them, times them? No, we just count again. Prime numbers, 2, 3, 5. Factors of 10, 1, 2, 5. The only ones that are both are 2 and 5. So probability of rolling a prime that's also a factor of 10, just 2 out of 6. And we could simplify that to a third if we wanted to. You'll notice I'm tending not to write these as decimals. I tend to think probabilities work better in fractions. Now if we do the same with a couple of other events here, and I just want to compare something here. We've got the event rolling a 5 The probability that actually happens is 1 out of 6 because there's only one 5 on a dice. The probability it does not happen, well, there's 1, 2, 3, 4 and 6. So it's a 5 out of 6 chance that it doesn't happen. If we add those two together, we get 6 out of 6 or 1. Okay, let's just see here. Probability of rolling an even number. There are 3 even numbers, 2, 4 and 6. So probability of rolling an even number is 3 out of 6. Probability of not rolling an even number, that's also 3 out of 6, the 3 odd numbers that we've been talking about. If I add those together, we get 6 out of 6, which is 1. Lastly, rolling a square number. There are 2 square numbers on the dice, 1 and 4, so the probability it happens, 2 out of 6, probability it does not happen, 4 out of 6, add them together, and again we get 6 out of 6 or 1. There's an important rule here that the probability an event does not happen is just 1 take away the probability that it does happen. So as well as theoretical probability, which is what we would expect to happen, we can have experimental probability, which is what has actually happened. The formula for experimental probability is very similar to the formula for theoretical probability. The number of times something happens divided by the total number of trials you did, as compared to the number of outcomes in the event divided by the total number of outcomes. Very basic example here, if we roll the dice 10 times and we got 7 odd numbers, we would say the experimental probability of an odd number on that dice is 7 out of 10. Now this can also be called the relative frequency, and will probably be more usually called the relative frequency. And there's just a point to make here that the more trials you perform, the more reliable this experimental probability, this relative frequency, actually gets. Okay, so let's look at an actual example that uses this terminology. We've got the classic XYZ trio, Xavier, Yvonne and Zoe, who perform an experiment on a bag of 100 coloured marbles, as we often do, taking out a marble, recording the colour, and then importantly, putting it back. We can fill in some relative frequencies before we answer anything here. Xavier has found 4 red marbles out of 5 attempts, so his relative frequency is 4/5, or we could put that as a decimal, 0.8. Yvonne, done the same thing, 16 out of 20, and again, that would simplify to 0.8. Zoe, 95 red marbles out of 100 trials, her relative frequency is closer to 0.95. Now that we've got some questions to follow up with this, the first question is to comment on Xavier's claim that the probability of choosing a red marble is 4/5. Now obviously that does match the results he's got, but he's not done very many trials, so we'd have to pick up on that. He's not performed enough trials to make a reliable estimate. What about Zoe's claim that the bag contains 95 red marbles? Well, she's more likely to be correct because she's done 20 times as many trials as Xavier, but again, it's not 100% true. We haven't looked at every marble, we've just maybe counted the same ones twice a lot. Thirdly, why is the most reliable estimate 0.92? Well, that's not actually something that's on the board, but we can do something clever. We can combine the 3 sets of results together. We can say that overall there are 125 trials and 115 red marbles, so the most accurate answer for this probability of choosing a red marble is 115 over 125, which is 0.92. Does the bag actually contain 92 red marbles? Well, again, it's more likely to be correct than Zoe, but we still don't know. Really important to understand about experimental probability, it's never guaranteed to be the actual probability. Okay, so let's look at another question. We've got a spinner this time, which we spin and get the following results. We want to try and complete this table. Now, you could try and work out the number of spins that are there. We can try and work out just what happens to get from 0.2 to 5. We can think about fractions. There's actually loads and loads of ways of attempting this problem. One way is just realizing that to get from your frequency, your relative frequency to your frequency, you times by 25. So I could do the same thing here. I could get that there are 10 blues, and if I want to go the other way, obviously I could divide by 25 and get that the relative frequency of red is 0.4. That's one option. Another way to do it would be to remember the probabilities sort of have to add up to 1. So at the moment we've got a 0.4, we've got a 0.2, they add up to 0.6, so the bit that is missing must be 0.4, and then we'd have to use the same methods we just worked out, or say, well, we've got 0.4, that's equal to 10, so this 0.4 should be equal to 10 as well. Third way I could think about doing this would be to think about fractions. We could say that 0.2 is 1/5, but if we remember the formula for experimental probability, it's equal to the amount of times something happens, which we know is 5 in this case, divided by the total number of trials. We can work out here that we're timesing the top of this fraction by 5, that we're timesing the bottom of this fraction by 5 as well, so there must be 25 spins of the wheel. That would give us relative frequencies of 10 over 25, which is 0.4, and then again we could use that to work out that there was 10 times that blue came up. Now the follow-on question here is to say which of these spinners below is definitely not the one that was being used, and you might be originally tempted towards this fella here because it's got a yellow sector, and certainly we didn't record any yellow results, but that can happen. Experimental probability isn't 100% reliable. It can have streaks and bias and luck. But what we can say is that this second spinner here definitely can't happen because we recorded some white spinner results, and this is the only spinner that doesn't have a white sector. So I would say something like this. And the final thing we can bring in from maybe year 7 and 8 probability is this idea of expected frequency, which is the number of times you would expect something to happen based on what's happened so far. We've got a general formula here again, that the expected frequency is equal to the probability of an event times the number of trials. So a very basic example, we would expect the probability of a head on a coin to be 0.5. If we did 300 coin flips, then we can multiply those two things together to get 150 heads would be expected. Let's go a little bit more in depth though. This is a standard deck of playing cards. There are 52 cards and they're organized into 4 suits, which from top to bottom are clubs, spades, hearts and diamonds. There are 13 cards in each suit. That means there are 52 cards altogether. Anyway, in this question we're told that we choose a card at random, record it and shuffle it back into the deck, and that we do this 200 times. So if we want to find an expected frequency for something, we're going to have to times a probability by 200. So to go through the list, probability of getting a red card, there's 26 red cards here, so we'd say 26 out of 52, and we times that by 200, and we get ourselves an answer of 100 red cards expected. Now you could a little bit more smartly say half the cards are red, half the 200 is 100. Probability of getting a club, well there's only one row of clubs here, that means there's 13 cards with clubs on. So the probability of getting a club is 13 out of 52. Multiply that by our 200 again, and we'll get that there are 50 club cards expected. Royal cards, that's jacks, queens and kings. There are about 12 of those here, I think. So we'd want to do 12 over 52 times 200. And that's equal to 46.2. Now, do we round that up and say we expect 46 royals or 47? No, we don't. It's just an expectation. We're saying on average, what would we expect to get? Lastly, getting a red 7, well, there are only 2 red 7s in the deck. There's the 7 of hearts, 7 of diamonds. So 2 out of 52 times 200, and that will give an expectation of 7.7 red 7s, which is nice. The last word we're defining here is bias, and bias is where one event is favoured over another, or one event is less favoured. We've got the results here for 100 dice rolls, which look okay for the most part, and we're asked, is this dice biased? Now what we'd want to do is figure out the result we'd expect to get. Each one has a probability of 1/6 of coming up if it's a fair dice. So if we do a 6th times 100, we'll get that we expect about 16.7 of each result. And for some of these, this looks fairly good. That's pretty close, that's pretty close, that's pretty close. These two are a fair away, but then they're just about acceptable, but this is the danger zone. That 6 is really not happening, so we'd want to say something like this, that we would expect 16 to 17 of each result, but that 6 is only happening a quarter of the time we expect it to. The dice is likely biased against 6. Now these next few slides are sample questions on the topic. I would suggest you pause the video on each page, that you have a go at them first, and that you see if your results match my results. Okay, I'm going to assume you've done that now. Let's go through. Sean's got a box of pens, 6 blue, 8 black, and 3 red, so that is 17 pens in total. The probability he'll pick a blue pen, well there's 6 blues, is 6 out of 17. Green pen, well there's no greens, so 0 out of 17 or just 0. Blue pens are added until the probability of picking a blue pen is a half. That means that half of the pens in total need to be blue. We know there are 11 pens that are not blue, so we need to match that with 11 blue pens, so we need to add 5 more blue pens. For the second question, we've got these positively numbered cards. We're going to assume they're whole numbers, I think, otherwise this gets a little bit spicy. We're told a couple of probabilities, and usefully those probabilities are out of 5, which just mean that that's the number of those things. The probability of 7 is 2/5. That means that there must be a second 7. The probability of an odd number is 3/5. Well, we've got our 3 odd numbers now, so we know that these two here must be even. We're told the range of the numbers is 10, and the probability of a 2 is 0. We can't have a 0 either, because that's not positive, so the smallest even number we could have would be a 4, and if we want the range to be 10, then the biggest number has to be 10 bigger than that, so it's 14. I think that's the only option, but let me know if you found a better one. Once again, pause the video here, have a go, and we're back. Okay, so again we've got a question here really about adding up to 1. So we're first asked what's the probability a student plays cricket. If we add up these 3 probabilities we get to 0.7. Cricket must be the remaining 0.3. We're asked if there are 650 students in the school, how many play rugby. This is an expected frequency, so we want to go the probability of rugby, which is 0.4, times the 650 students that actually play it, and we would get that there are 260 that play rugby. We're then asked about the rugby team that has this particular probability of results. We've got win 0.4, draw 0.35, and lose is going to be 0.25 because again these all need to add up to 1, and that was 0.75 so far. They play 25 games in a season, and a fifth of them are called off, so we can immediately figure out what that is. A fifth of 25, that means that 5 games were called off. A win is worth 4 points, a draw is worth 2 points, and a called off game is worth 1 point. We want a number of points, so we need to figure out how many wins, draws, and losses we actually expect. If we expect them to actually play 20 games in the season, because 5 of them have been called off, we just need to multiply our probability by 20 to get how many wins, to get how many draws, and to get how many losses. So you can see there we've got 8 wins, 7 draws, 5 losses, and 5 games called up. They all add up to 25, so that seems okay. That will give me 32 points for 8 wins, 14 points for the draws, 5 points for the games that were called off, and presumably 0 points for all those losses. A total of 51 points expected that season. Okay, once go, make sure you have a go first. And we're back. In this case, the first few questions are fairly straightforward. David 3 out of 20 or 0.15, Becky 11 out of 100 or 0.11. More reliable estimate will be the person that does the more trials, so it's just Becky. Now the most reliable estimate we could make would be if we put both of their trials together. So we could say, okay, that's 120 trials in total, that's 14 yellow jelly beans that were selected. So if we want to use that probability, 14 out of 120, multiply it by the 500 beans that we know are in the tin, we could expect there are 58.3 yellow jelly beans. Now we might round that to 58 if we were actually making our guess in the game. Okay, another thing you can do with relative frequencies is plot graphs of them. Again, have a go first. So the first thing I'm going to do is fill in the relative frequencies here. And in each case, all I'm doing is dividing the amount of A's by the number of spins. 5 over 10 gives me 0.5, 12 over 20 gives me 0.6, etc. Second thing we're going to do is plot those on the graph. So after 10 spins, we had a relative frequency of 0.5. So we'll make a mark at 10 spins and 0.5. And we'll do the same thing with the other values that we've worked out. So 30 up to 0.7, 40 up to 0.65. Technically, to complete a relative frequency graph, we should then join those together with straight lines. Now, David says the relative frequency after 50 spins is 0.8. Why is he definitely wrong? Well, how many spins would that be? We can actually work that out. We multiply the probability of that happening, which is 0.8, by the number of spins, and that would say that there were 40 40 A's that we've actually got on this spinner. But if we look at it, after 40 spins, we only had 26 A's. We're not going to be able to get to 50 and get that up to 40 because it would mean spinning an A more times than we've actually done spins. Okay, lastly we have James's adventures with Lego bricks. Have a go first. And we're back. So we want to find how many white bricks James found in his first 20 trials. 20 trials is this blue square down here, and that goes to a relative frequency of 0.15. So the amount of white bricks he found was the probability times the number of trials. He found 3 white bricks. What's the most reliable estimate for the number of white bricks? Well, the most reliable estimate is the 0.2 relative frequency. So we would have to explain that we're picking the one with the most trials. And then the calculation we would need to do is 0.2 for the probability that we get a white brick. And then there are 4,000 bricks in the actual box. So 0.2 times 4,000 gives us a total of 800 white bricks. Explain would be that that's where we did the most trials. So that's it for this week. Next week we'll look at some slightly more in-depth probability sample spaces, tree diagrams and the like. But yeah, see you then.